applying an acoustic model and a language model. So what the acoustic model in traditional ASR approach does is it gives you a probability for the feature representation F for a particular transcription. Now the first, this looks a little bit odd, really, right? Why would you do that? The advantage of that is that you can apply Bayes rule. So if you take the product between PF given W and PW, which is the probability of the language model, then you can get, then basically you can apply a Bayes rule here. This is the original, that's the motivation for that. And what we do is we look for different W's, transcriptions, that would best explain the feature representation F. So we can estimate this acoustic model F given W from paired data, where we have both a transcription and a feature representation. And the language model we can simply estimate from just text, web text, whatever text you want to use for your application. And you can use, if you want a large language model or a traditional Ngram-based language model, it doesn't matter. And then if you have that, you try to find your W star, which tries to find, which is basically like the transcription W that will maximize this product between the acoustic model and the language model probability. So that's a slide with the most formulas, just as a warning. So that was pretty much it, I believe, and the rest should be more straightforward. So how do we represent actually these transcriptions? Well, typically what's done is instead of directly outputting words, we output a sequence of phonemes. So W is a sequence of phonemes. And what is a phoneme? A phoneme is basically a distinct unit of sound. So if you think about any word, it has different sounds in it, and this is what these phonemes basically denote. So for example, hello, you have the H sound, L, O, right? So you can break it down like this, and you can do this in every language. And that's how typically traditional speech recognition systems are being built. They don't output actual words, but rather these phonemes that can then be converted back into words. So now, because we don't use words, we also have this pronunciation model that produces these phonemes Q, and there can be more than one way to break down a word sometimes, and this is where we sum over the possible pronunciations. Now, so much about how the typical machinery works in speech recognition, but there's also the feature representation at the bottom, which I didn't talk very much about, but this is what will be the rest of the talk will be about, how to learn this feature representation. But traditionally, these feature representations have not been learned, they have been handcrafted. And what people do is they record speech with a typical sample rate of 8 or 16 kilohertz, and then they build what's called a spectrogram. So a spectrogram is basically something that looks at small windows of the waveform, about 20 milliseconds, so very, very short, right? Shorter than many phonemes actually are. And then what they do over this window, they compute a fast Fourier transform and take the magnitude. And you can think about the output of this as simply describing the frequency content in a 20 millisecond window. Now you have this description of this 20 millisecond window, giving you an idea of how the frequencies in the waveform are distributed for this window, and then they are just being concatenated together. And that's what the feature representation traditionally is. So it's basically based on fast Fourier transform. Right, and you concatenate them together, as I said, to get your features, yeah. So What I will talk about the rest of the talk is how to learn these representations instead of actually using an off-the-shelf fast Fourier transform, and how to learn it and why that can be a good idea. So we apply self-supervision to learn good representations of speech. So traditionally, how people trained machine learning systems or even speech systems is using supervised learning. And supervised learning is based on having lots of examples of input-output examples. So for example, if you want to learn what a cat looks like, we might have an example of this first picture on the top and the label cat. And we collect lots of these examples and then train systems using this data. Now, the problem with that is that you may not have collected enough diverse examples of cats, because there's many different cats and cats doing very strange things, for example, like here, and at the bottom picture. And you may then see that your classifier cannot correctly identify the cat at the bottom simply because it hasn't seen a cat in a box. So apart from that training test mismatch, there's also the issue that you need to annotate a lot of data, of course, by hand, oftentimes, as is done in speech, because you have like somebody, either somebody reads out a piece of text. This is one way to generate speech data. So for example, somebody may read the sentence, need to annotate lots of data, and then you have both the text and the speech. Or the other way around, you take what somebody said and you then write down the text transcription. And people do both in practice, but either one of those requires additional effort. And aside from this, to basically teach a machine explicitly that an input example corresponds to a particular label or transcription or sequential output, that basically that this is purely how we as humans learn is very unlikely. So typically, people don't just learn by like explicit supervision, as would be the case here. The way people learn a lot is by listening to others around us, right? So for example, when we try to learn a new language, it is very helpful to listen to native speakers to get a bit of idea, like how do these words sound, etc., etc. And we don't just learn everything from being given explicit instructions or labels, as would be the case in supervised learning. So this contrasts to self-supervised learning, where the idea is to learn a lot about the problem that we're trying, or data that we're trying to handle, rather, without labels. And in the case of speech, what we would do is we actually would look at a lot of speech audio, the waveform, and try to learn good representations of that. Now, another reason why self-supervised learning can be very useful is because typically we have a lot more unlabeled data than we have labeled data. And if we can effectively use this unlabeled data and learn a lot from it, then we can use the resulting representations to solve a particular task and make better use of that labeled data that we also have. So we can use both instead of just relying on the labeled data. So one way to think about this is think about supervised and self-supervised learning is that in supervised learning, we're trying to do two things at the same time. In supervised learning, we try to simultaneously learn how the data looks like, so how the input looks like, how do cat pictures look like, or like pictures in general look like, and try to associate any kind of representation, and by that I mean the activations in a neural network, how they are associated with a particular output, for example, like a label cat. So we're trying to get a feel for the pictures themselves and also trying to associate them with a particular label. And a major limitation of supervised learning is that we have to rely entirely on label data to learn a feature encoding. So like feature encoding means how pictures look like in some sense. And in self-supervised learning, in contrast, what we are doing is we are trying to separate these different steps. So first, we're looking purely at unlabeled data. We're learning a feature encoder. That's the first step, and we do this because we do not need any labels for that. So we do representation learning. And then once we have the self-supervised learning step is completed, then we can learn a classifier on top of this data representation we learned to associate this data representation with labels, i.e. that this picture would correspond, or the representation of this picture corresponds to the label cat. And this also reduces the reliance on labeled data. So going back to speech, or relating this back to speech, the way speech systems or speech recognition systems here more specifically are being typically built is by collecting literally thousands of hours of transcribed speech data, and then using that to train one particular speech systems for one language, most likely one accent and one particular domain. So people, for example, maybe reading the news, which is different from people giving talks, from people having, phone conversations, etc., etc. So these systems often tend to be very narrow, as has been shown, right? So if you have a slightly different accent, or if you have a little bit of background noise, or talk about different topics, then these systems suddenly start to work less well. And this really becomes a problem because we have, 7,000 languages in the world, and many different domains and even more accents. And so this makes this traditional approach of supervised training with lots of data very, very brittle and not very robust. So instead, what we can try to do, instead of just relying on these thousands of hours of speech, is to use self-supervised learning to learn from unlabeled data that can then basically produce a feature representation. And I'm showing this this pre-trained model that was produced in self-supervised learning here. I'm showing the output as simply as a list of numbers, which is actually very accurate. It just produces a feature representation, and that's what that is. And then when we have that feature representation, we can then use that to learn different classifiers that can perform different tasks, going back to that slide I had initially. So we may perform the task of speech recognition, transcribing text. We can use the same features to translate into a different language, translating English into, for example, German here. Or we may just simply detect what type of audio is being actually, the model is being presented with. Is it music, or is it speech, or is it just silence? So we can use such a model for many different tasks, and the model we developed for that for producing these features is called wav2vec, and I'll talk next about that. And before I do that, maybe I stop and take any questions, or maybe we can do the questions at the end. Okay, let's do it at the end. Sounds good. So the model that we developed is called wav2vec. So let me explain that model a little bit. So that model, in a nutshell, is actually very similar to BERT, which was developed for text. But let me explain it in detail. So what we want to do is we want to learn something that can encode audio data, specifically speech audio data. And I represent that as we have a raw waveform here. For example, me speaking, which I denote as X. And then what we do is we encode it with a multi-layer convolutional neural network actually into something we call a latent speech representation. But at the end of the day, it's still a bunch of each one of those triangles still outputs a vector. And we run this convolutional neural network, and I think it has about 7 layers. And what it does is it takes a 16 kilohertz speech signal. So that means 16,000 numbers that indicate the frequency, and basically that is being downsampled to 20 milliseconds. So it's 50 hertz. Sorry, 50 hertz. So it basically this CNN really is sort of a bottleneck and gives us then a vector every 20 milliseconds. And as a next step, what we do is we input a transformer. We input this sequence of vectors into a transformer. Now, you will talk about, I think you will learn about transformers later this week, but for the purpose of this talk here, just think about it as it's just another building block, another type of model that enables us to encode these speech representations and transform them further, just as a few more layers in our neural network. And in order to learn something from this data, what we do is we basically mask some of these latent speech representations. So what does that mean? So before we feed these squares, these blue squares into the transformer, we simply remove some of them. They're just gone. So then the transformer doesn't know what's behind those, what's actually in the data there, because it's those vectors have been removed. And what that transformer then does is it outputs more representations, but these representations have been, in some sense, they can see the entire sequence, because that's what transformers do, and you will see that later. So they can basically contextualize these representations. That's a technical word. And then what we want to do is we want to set up a learning task. Well, there's no learning task yet. What is this model doing? Well, we removed some of the input data through this masking. And then the job of the model during training is to predict those missing parts of the data. But we don't directly predict the actual data. We predict something we call speech units. So if you think about speech, right, it's this signal of, so we have these 16,000 integers, right, for each second. So we could just try to reconstruct each one of those for the missing parts, but that would be a very difficult task, because there's a lot of things to predict, and then the model would get penalized for just getting it a little bit wrong, etc., etc. So what we wanted to do instead is we wanted to learn an inventory of speech units. So for example, in text, what we have is we have a certain vocabulary. So when you read some text, you recognize words because you have seen them before. So there's an inventory of words in any language you will speak. And so we wanted to learn something similar for speech. And the way we do this is by taking those squares, those blue squares, and by quantizing. So what that means is, so each one of those squares is it's a vector of numbers. That's what's output by a convolutional neural network. And what quantization means is that we assign each one of those blue squares to an inventory of fixed units. So we could have, for example, 100 different units, and then each one of those vectors is assigned to one of them. It's specifically the one that is closest in the inventory to that blue square that we are currently dealing with. So there's some similarity. It's not really search, but like we are basically reducing the number of possible squares that our model can represent. And that's what the Q is doing here. It's basically taking that square, looking up what's the closest one in an inventory that we learn of speech units, and then we try to predict at the top with a contrastive loss, and I'll talk about in a second, which one of those quantized units is behind a masked one. So we're not really predicting the actual waveform, but rather like a discrete representation of it. So this learning task here can be seen as a joint vector quantization, and this is the process I just described of having this kind of inventory of speech units, and also context representation learning, which is what the transformer does. And the way we train the model is by contrasting the true quantized latent, so the one that is the thing that's behind the masked time step, the square, the quantized one, with potential alternatives. So what does that mean in practice? So looking at the loss here, and this loss is very similar to what people have used in the computer vision literature. We basically compute a cosine similarity between what is output by the transformer, which is the CT, and I'm talking about the numerator here, and then discrete latent speech representations, which is basically what the Q produces. So that will be a square that has been assigned to that inventory, and then it's basically a number. Well, it's not a number, sorry, it's a representation for that quantized one. And then we have in the denominator simply some alternatives that we contrast the numerator to. The job of our model is to make the numerator as large as possible, and thereby reducing the loss. And what that means is to make it as large as possible means to correctly identify what is behind that mask time step. So you can think about this the same way as trying to predict what is the correct word in a sentence that has been removed in some way. That's what the BERT models do. And one way to our model could cheat here is by simply just learning that there is only a single codebook entry. So there's only a single word in our speech unit inventory. And one way to counter that is we introduce a diversity penalty to make sure that our model uses those different entries in the codebook as much as possible. Okay, so this is the training. Actually, hold on. That's also the masking. So we need to mask some of these time steps. As I said, some of the data, and the way we do it is we have these 20 millisecond blocks that I mentioned. Each square is 20 milliseconds, and we always mask 10 of those in a row. And the reason we do that is because 20 milliseconds is really short. It would be very easy for anybody to predict for the machine and for us as well what the next 20 milliseconds look like. So this is why we mask about 10 to make it harder. And what we do is we mask about half of all the squares in our typical training example of 15 seconds. And so that about 300 milliseconds of each one of those mask spans is about 300 milliseconds. So once this model is trained, so once we have done the self-supervised learning, then we can go back to actually fine-tuning it for a specific task. So we can apply, for example, for automatic speech recognition, we use the standard CTC loss, which is a standard loss. I'm not going to go into detail here. And we apply standard regularization, and we don't use any quantization or any of the contrastive loss. we simply just try to associate these context representations at the top with particular labels that we would like our model to output. So for example, words or characters, and sometimes even phonemes, depending on the task. So yeah, for example, here we may associate teach the model to output characters. So how well does this work? So at the time when we did this, this model, which is about, actually it's 3 years ago now nearly, there were a bunch of existing systems, and I'm showing here the word error rate for them, including our model. And here you can see the word error rate on the Libri Speech benchmark, which is a benchmark of read audiobooks in English. And low word error rate means better performance. And you can see the word error rates are already pretty low here. Like, so they range from 0 to 100, and sometimes, yeah, about 100, think about it like that. So they're pretty low. The existing best supervised systems had a word error rate about 4.1, and that could be improved by a clever use of unlabeled data to about 3.4. And the way people did do that is by taking, in addition to this 960 hours, they took about 60,000 hours of additional data, where there were no transcriptions for that data, and then labeled that with that supervised system that I'm showing here, this context net, and then retrained the system, and that improved the word error rate a little bit. And we contrasted that to our model that had that used these 60,000 hours differently, by simply doing the pre-training that I described in the previous slides. And then we fine-tuned that model on that 960 hours of labeled data. And we can see that the wav2vec approach does about similarly to that existing noisy student approach, that semi-supervised approach. And that shows that that was the first time that self-supervised learning actually was shown to work as well as existing systems in a high resource setting, where you have like 1,000 hours, which is quite a lot. But where it gets really interesting is in settings where you don't have 1,000 hours of labeled data, where you have a lot less. And that's the scenario we find ourselves a lot in practice, particularly if you move to different dialects and languages, etc., etc. And what I'm showing on the right here is the performance of this noisy student approach, which basically uses, I think it's 960 hours unlabeled in this setting here actually, to label that again, and so the model is trained on 100 hours of labeled data, and then you label 960 hours of unlabeled data, and you retrain, and that gets a word error rate of 8.6. And if you use 960 hours of unlabeled data with wav2vec, and that's the light blue bar, and then fine-tune 100 hours, you can do a lot better. And that was actually very surprising at the time, that you could do a lot better than this approach. And the reason is because self-supervised learning is really good when you don't have a lot of data. When you have a lot of data, it can still work well, as I shown on the left, but it really shines when you have little data. And that's a scenario we find ourselves a lot in speech. And the orange bar here in the middle shows when you just use 1 hour of labeled data. So instead of using 100, 1 hour, and this still does better than the noisy student approach with 100 hours. And if you use 10 minutes of data, and 10 minutes of data, to give you an idea, that's about 40 sentences, people speaking 40 sentences, and this is how you train a speech system. You do a little bit worse at 10.8, but it's still remarkable that that worked. And if you use more unlabeled data, that's the last bar, instead of 960 hours, you use 60,000 hours, you can get back to the performance of the noisy student model. So you can do better than the best system at the time there, with just 10 minutes of data instead of 100 hours. So this shows that self-supervised learning can be effective for both high and low resource settings. Right. Let me skip over this slide here. And just to give you an idea what this looks like here, what these models produce. So this is a model that was trained with just 10 minutes of labeled data. So 40 sentences of data. And what I'm showing I'm showing two examples here, and for each one, for the top one, for example, the first row is the output of the model, the hypothesis. We call it hypothesis for an utterance with no language model. So typically we use language models, and you can see that the transcription is very you can sort of understand what's being said. Yeah, but with a language model, it can get better. And there's still a few errors, but it's nice to see that you can get a usable, or close to usable transcription with just so little training data. So what I'm showing here is sort of the equivalent of the ImageNet slide for speech. And what that means is I'm showing here the performance of different systems. You can see that at the bottom on the x-axis. Over time for the past, at the time it was about 5 years, in speech, where the word error rate on this Libri speech benchmark that they've been using so far has sort of steadily decreased. And at the top, I'm showing the amount of label data that is used for each one of those systems. So typically systems use 960 hours or more. So for example, Deep Speech 2, the first bar, uses a lot more than that. And then I'm showing in blue here the results with this wav2vec 2.0 model that are presented. And you can see that if it just uses 10 minutes of label data, it doesn't do as well as the best systems. But if you use, for example, in the last bar, also self-training, which is what the noisy student approach that I discussed in the previous slides does, then it can do basically as well as the best system that was developed 2 years earlier, but using only 10 minutes of labeled data instead of 960 hours. And also, you can see that even the best systems today that use a lot of labeled data. So this is the third and the fourth last bar. They use wav2vec. So another follow-on project we did from that was to learn multilingual or cross-lingual speech representations. So far I've been talking about English. Everything was about English. And I've been talking about that, we have many settings where we don't have a lot of data, and that's particularly the case if you move out of English or a handful of languages for which a lot of data exists. And this is where this project comes in. So the idea of cross-lingual self-supervised learning is to learn representations that work across many different languages. The motivation for doing that is that if we have little label data, like is the case very often, then we also have little unlabeled data. We usually have more unlabeled data than labeled data, but there's still less than in high resource languages. And the general idea is to leverage the general idea of cross-lingual training is to leverage the unlabeled data from high resource languages for low resource languages. And then there's also the aspect of having different models for each of the many languages we have. So for the 7,000 languages, having a separate model for each language, for each domain, for each accent. This is just a lot of different models. So maybe we can have a single model for all the different languages that you're going to deal with. And this is something that sounds maybe a bit crazy, but this is something that's has become more and more popular in other fields. So for example, in cross-language text understanding, this has been very widely adopted and has been very successful. Similarly, for machine translation, we have many different languages, and people are moving more towards having systems that can translate between many different languages to many different languages, instead of translating from one language to another language, and then we have to train another model for a different set of languages, etc., etc. So what we did quite a few, this is actually now, I think 1.5 years ago, we built a model that was trained on 128 different languages and over 400,000 hours. We actually, just a month ago, did a follow-on project to that where we expanded this to 1,400 languages and 500,000 hours of data. But I can send you a pointer to that, and I will not talk about that today. But the idea is similar. We have a large number of languages and a very good amount of data. And we pre-train a model on that. And the general idea is that we just take data from many different data sets. So for example, multilingual Libre speech, which covers 80 languages, or Vox, or like, let's say, Babel, which has 1,000 hours for 17 languages. And what we do is we just take this data and we train a wav2vec 2.0 model on that. And the trick here is, well, there's actually no trick. That's the beauty of that. We don't even tell the model when we train on data from a particular language, or we just mix the data and we train the model on it. We do change the sampling a little bit, but our model doesn't know what language it's dealing with. So sometimes it has examples from English, sometimes it has Swahili, sometimes it has Amharic, and the list goes on. And it doesn't know that it doesn't know information what language it's dealing with. So it simply tries to solve that task that I described earlier. And then we simply fine-tune this model for a bunch of different tasks at the end. So we evaluated this model on a few different tasks. So for example, on speech translation, so translating the speech in one language to others, also speech recognition, language ID, etc. And where we found it being most effective was for actually speech translation. So taking speech in a foreign language and translating it into English. And here I'm grouping the results into, so this is 15 different language directions. So translating from, I believe, let's say Hindi to English and 14 other languages. And then we group them into high resource, mid resource, and low resource, depending on the amount of labeled data. And we found actually that the highest improvements with this approach came when in settings where there's very little labeled data, very consistent with what I said earlier. In the high resource setting, there was actually a slight, there was still a bit of an improvement, but most of it was really in the mid resource and particularly the low resource setting, where we moved from some languages not working at all to actually being usable. And there were similar nice improvements on speech recognition for example, Assamese, Tagalog, Swahili, Lao, Georgian, etc. And when we trained this model, we produced these quantized representations. So what that means is these units of speech that you can think about like words, although they only represent about 20 milliseconds of audio. And those units are being shared across languages. So for example, we may take units, we have units that we see both in English and Chinese, or both in Chinese and French, for example. And we use those units to better understand, to see like how our model does shares representations across languages. And the way we did is we simply plotted how these representations, or on average, are being used across different languages. So, for example, we can see here that that Italian and Basque, or like Italian and Catalan or Spanish, tend to use units at certain units at a similar rate to each other. Same for English, German, and French. Chinese and Mandarin, and it's not perfect, as you can see, right? Because there's quite a distance between between the two Chinese, not really dialects, but variants. But you can. This is something that is automatically learned, right? So it's not perfect, and there's no supervision in doing it. What we can see is that there are certain patterns, but they are certainly not perfect. Okay, maybe let me stop here actually, because I think that's a good amount of content we discussed. I think this wav2vec has been really the first time that pre-training for speech has been shown to work really well, both in the high resource, but particularly in the low resource setting, where there's a lot less than the 1,000 hours of data that people typically use. And what self-supervised learning enables is that being able to use only about close to 50 utterances, people speaking 50 sentences of data can do as well as some of the best systems from only a few years ago that were trained on close to 1,000 hours. And if you're interested in this, then you can find the code and the models on the FairSeek GitHub repository. It's also on Hugging Face. And I'll just take a look, just have a look for like wav2vec and FairSeek or Hugging Face, and you will be able to find that. Yeah, maybe let me end here and take any questions that people may have.
Can you hear me?
Yes.
Okay, can you hear me? Sorry, we had to mute you so we can speak, so we can't talk at the same time. So thank you for the talk. Especially, it's really relevant to Mongolian language because it's very low resource language, and it's amazing that 10 minutes of speech is enough for achieving these results. And while we're gonna learn about transformers and this language model in a few days, so I think this is gonna make much more sense in a couple of days. So yeah, thank you for the talk. Yeah. So any questions you can ask in English.
Can you hear me now? In order to decrease the word error rate into less than 10% or 5%, how many hours of data do I need? Because I trained wav2vec on common voice data, and it was 48% of the word error rate. How many hours of data do I need?
So the question is how many hours of data you need to achieve less than 10% accuracy. Okay, hold on, let me mute this so you can speak.
Yeah. Can you hear me okay? Good. So it's a really good question. It really, so you won't like my answer. So there are some languages for which, the word error rate is just always higher. And it's just because these languages are more difficult. And it really depends on the language. It depends on the domain. So for example, somebody reading out a book, speaking very clearly in a good studio recording, you should be able to get a better word error rate than when you speak on your mobile phone, right? Somewhere on the street in a noisy environment. So it really depends on that, right? It's very hard to say, but the general rule is the more data, the better. I can't tell you how much. I can tell you though that there's some languages for which we have a good amount of data, but we don't get below 10%. It's just too difficult. And because it's just it's not this clear audio, this clear recording studio environment, etc., etc. It really depends. Yeah, sorry, I don't have a bad answer for you.
Okay, so if there's any other question.
Монголоор ч ямар нэгэн бусад хэлбэрээр ажиллахдаа өөр нэг хэмжээ оролцоогод үгүй гэж хэлсэн юм уу? Юм лангуужууд одоо сүүлийн хэдэн ямар ч тийм лангуужийг тодорхойлохгүй маань хэл сайн төгссөн байх.
So the question, can you hear us? Can you hear us?
I can. It was just a bit choppy.
Okay.
If you could
So
repeat.
the question was, when we speak in one language, like in Mongolian, but when we use other words from other languages to English words, these unsupervised methods, how well they handle these other words, happening used in another language. Does that make sense?
Sorry, can you say it again?
Wait, hold on. Let me just put you on.
Oh, sorry. Can you repeat the question again? The line was a little bit choppy. Apologies.
Sure. So the question was, when we talk in one language, in Mongolian, for example, we use English words or another language, words from another language, and how well the unsupervised methods handle these situations.
Yeah, that's an excellent question, right? I think it depends on the training data, right? In some sense, right? So if you train a system on just Mongolian data, people speaking, let's say Mongolian or any other language, it doesn't matter, but just one of them, and this training data never has any English words in it, then there will be trouble. Then the system may be outputting stuff that is not so ideal. But if people have, if in the training data there's some English words in there, then the model will have been exposed to this, and it should be able to transcribe those words. It gets even more interesting if you have a multilingual model. So one of the things we worked on recently is to train these multilingual models that can support up to 1,000 languages, right? And there, the model in theory can transcribe all these different languages, right? But you have then the problem of the person, let's say, speaks Mongolian, then they say an English word, right? And then they go back to Mongolian, right? But that's something that we have not trained the model to do, right? So this is something, it's a little bit uncharted territory, right? So getting this right is something we have not really focused very much on, but that's very interesting future work. And this is known as code switching, right? Because you sort of switch between different languages. So it's a very interesting area of research. We haven't focused that much on it, but I would say the simple answer is if you have trained your system to do that, if it has English data in the training data, then you have a better chance of it being able to do that than not.
Okay. Any other questions? Okay.
So first, thank you for the
Okay, really sorry. So the question was, word tokenization is really important for language modeling or on a text data. And the equivalent here is the window, 15 millisecond or 20 milliseconds of windows. And that number doesn't in the language comes up. That was the question. So does it depend on the language itself or what kind of the model we are using? So, does it make sense?
Right.
Okay.
So hold on.
All right.
Are you asking whether the size of the 20, whether it should be 20 milliseconds, if that depends on the language or?
So is I think there's some delay here. Can you hear us?
Yes, I can hear you perfectly now, yeah.
Okay. So does it depend on the language or does it depend on the architecture, the model architecture?
Ah, it looks like you got kicked out again. It's a model architecture that we found to work well. Oh, I see. So sorry, I was told you can hear me. So these 15 milliseconds that we chose there, actually it's 20 milliseconds. This is something that's because we designed the model architecture the way we did, and we found that this works very well. Other choices are not much worse, but we found that to work fairly well. It was a decent choice. It's not language dependent. We use that same architecture for many different languages. Now, that doesn't mean that a slightly different one couldn't work better, but it served us well so far. Oh, it looks like it's breaking up again. The video is paused.
Okay, thank you for the talk. I think it's for me is activity. So why do we not here?
Okay. Can you?
It's the same thing. The inventory of speech units is what we do is we pick for each one of these 20 millisecond windows, we pick in some sense one unit, and you can also call it a token, but that's what we do. So they are the same thing. You are muted at the moment, just in case you're wondering.
Okay, so the question was, when you have suffix into the words, especially in Mongolian language, the word changes as you add suffixes. So do you do you separate them in the model? If so, yeah, do you do it separately? And what if the pronunciation changes because of the suffix of the word? Because of something is
Yeah.
added to the word? Oh,
Yeah. So, yeah, morphological rich languages, right? They pose very interesting challenges. So the way we go about this is, so for example, large language models, they have this subword tokenization, right? So one word might be broken up into, like, with a word with 6 characters might be broken up into 3 different units, right? But we go even further, we just model individual characters, okay? Now, for English, that makes a lot of sense, right? But if you move to, let's say, languages with very interesting vocabularies, let's say Chinese and so on, right? Then we just model each individual symbol, right? Each individual character there as well. So our model is really fine-grained. So in some sense, this is how that is taken, how this is addressed. Let's put it this way.
okay, I think so. We're gonna end here. Let's thank the guy again for the great talk. Okay.
Well, thank you for having me. It was a pleasure. And if anybody has any questions or anything, then feel free to email me. You can find my email address on my homepage. Feel free to reach out about any questions or anything in case you're interested. Okay, bye.